so it's my pleasure to introduce Junho, who will tell us today about BFN definition of Coulomb branches.
Thanks for the introduction, and thanks Daniel for organizing, and thanks everyone for coming. So finally, we will talk about Coulomb branches today. So I'll drop adjectives because I don't understand them. Just a spoiler, it'll be some algebraic variety that has reasonable geometric properties. And in fact, an affine variety. So we just have to define what the ring is and have to see that it has the properties we want. Okay, so first reference is Braverman. Not the G1. Words. It's a little long, but a mathematical definition of Coulomb branches then too. So the first one is more like just by Nakajima, more physics-like. I tried looking and to understand it. But the second one is what we're going to talk about. And I'll just give like a skeleton part of the theory. So there will be a lot of things that I'm not going to talk about today. Okay. Maybe let me just just to orient ourselves. So we want to define some ring, which will be commutative ring, and we want to define Coulomb branches as just spec of A. And so what is this ring? It's going to be some equivariant Borel morphology of this geometric thing, which they call a variety of triples. So it is an analog in some sense triples of maybe the more familiar one in the finite dimensional story of Steinberg varieties. So we want to define what this space is. Okay, just that was very brief orientation. So let me recall some notation, and I'm also going to use some notation that are slightly different from what Elenan did, like just a little bit. So let G be say connected. They say it doesn't matter, and it seems like it doesn't matter. The group for us it'll be over C, and O will be the power series ring. So just recalling definitions. Okay, it's filled with fractions. So Lorentz series. And then D is the formal disk. And D star is the punctured one. Okay. And I think Elhanan used LG and L plus G for loop groups and positive loop group. We will. I'm just going to use this notation that they use, which is GK. There is a stack GQC, which sends a C algebra to G torsors over the disk. Wait, okay, that's LG, so we start. B star R just means phase change to R. Plus G is GO. So okay, let me write this first. It's the same thing, but for over the R, the not punctured one. And as we saw, the stack quotient is the affine Grassmannian, and the moduli description is it is a pair where this P is a G bundle G torser over the disk over R with trivialization the POPR over the puncture disk. So P star R going to G times the trivial bundle, and it's more physics. So that's what, yeah, and yeah, everything is static. Oh, so should I start using that? Okay. Okay, so and just a quick comment is that we're going to like as in the paper, we will kind of confuse in notation and in language like the C points of some stack and just the stack. I might just do that without saying, but like it shouldn't cause any confusion. Okay. So that's all from last time. And now let's add be some finite dimensional representation of G over C. So we want to I want to define what that R is. It's some type of like kind of very large space, but it's not like that horrible. So to do that, I want to define some like a somewhat auxiliary space. And I'll define what kind of object it is. So T is this moduli stack of so like the same data as the affine Grassmannian, P and P, and then some section. Okay, so so P is just some okay, so INC algebra, let me just suppress like this if that's okay, because unless there is like a okay. And S is a section of associated vector bundle. So P is from G torser, so we can form a vector bundle like this. Or H0 of this thing. Yeah. And let me call this P sub n. All right. Okay, so what kind of space is this? Well, just by the moduli description, it is clear that this thing has some map, let's say small pi to the affine Grassmannian. So like to give it away, it's some infinite rank vector bundle on affine Grassmannian. Okay. And fiber, clearly the fiber over some P5 is given by the space of global sections of this Pn, and rank is infinite again. Okay. So and then I'm going to say, oh, okay, let me so we have this trivialization So let's restrict that vector bundle to the pointer disk. And we get a trivialization of vector bundle over the pointer disk, which we denote by Tn. And I'm going to use this to define the variety of triples as some closed offset given by the same kind of triples, except requiring that. So if you look at this is some infinite rank vector bundle over a pointer disk. And if you try to extend it towards the origin, it might have some kind of pole. And what I'm requiring is that it does not have a pole. Requiring that E and S. So for any S as above, extends to a regular section, not just meromorphic. A regular section for the entire puncture disk. Well, let me say D. Okay, and that's equivalent to saying that this is an O rather than just NK. Any questions?
So is it true that the fiber of this T is NK?
NK.
Like
right, so I mean
H0 of Pn is an abstract description, but I think it uses
right. So it's more or less like something I'm going to say.
okay.
Oh, yeah, I mean, okay, so like just to answer it right away, it's and I mean PK mod geo is fiber smiley.
And O.
Oh, and K. Maybe I'm and I think it's yeah.
Oh yeah, of course.
Yeah.
So if you choose some trivialization, not this fine, but some other trivialization, then you can send it to just okay.
That is correct. Yes. Yeah, I mean the confusing point I think that you were well, okay, let me just like say it. Well, I already wrote. Well, let me just rewrite it. So it's from the modular description. T is this product, which is just usual product, but then you do, okay, let me write it like this. You just do the quotient by geo along diagonal and way, as usual, in the usual way. So we'll keep using this notation bracket. So this is G as pair to equivalence relation G B inverse B S is equivalent to GS and E is in GO. And note that, I mean, it's convenient to notice that the product, if you just multiply it in this order, that's multiplying always for any representatives. Okay, is there any question? And so N is some vector space, right? And then just similarly as before, consider this function. It's so make it as, you make it as stack, and then it also, you can think of it C points, and which is literally what's kind of written here, except C. Same thing with MK, but power series. Just same recipe as GK and GO, which are right, okay. And so there's this description, but then you also have so this map, as I said, the product is well defined, so you can take it, which is really just Pn of S. So G is in GK, you just multiply GK part to NO, and then it might leave NO, but it'll be something in NK. It might introduce some pole because GK, if you take like a sequence there, it can have like some poles. Okay. Okay. So yeah, this way you get closed domain. T. So we use the projection to a Van-Grassmannian, and then this map to NK, and then that gives me a map from T to the product of Van-Grassmannian and then NK, and this is a closed domain actually. Check it on some test rings, and there's a closed condition. And then in this description, so we said earlier that R is the ones where PNS doesn't have a pole, right? PNS is exactly this thing. So in this description, R is exactly T intersect with GRG, and now this NO. Let me know if there's any question, or you want me to start? Oh, wait, so how do I make it like more audible?
I think it's Gus. Is it working?
Comment of the different effects, I think it's that people mean when they talk about ravioli or raviola, right? Something
Gus, sorry, something is like my volume is a maximum, but maybe some other mic position or something. We hear you, but it's very noisy. I think my okay. Yeah, could you? Never mind, please. Yeah, could you maybe write it in chat, and
maybe I can check later.
I'll just read it out. Yeah, thank you. Yeah, I'll.
So T visibly has an action of GK, just multiply on the left. And if you do it with GO, then that preserves R.
Maybe could you maybe comment a bit about this isomorphism of T, like the T equals
this?
why are these two descriptions equivalent?
Oh, wow. Okay. All right. So okay. So this description is more or less spelling out the moduli description. I little more. I can say a little more. Because GK mod GO is a Van-Grassmannian, right? And then but I think what you were trying to say is why this is okay. Let me see. So
Yeah, just like I mean, we don't just that this action, like in one sense, it's left multiplication, but I think on the other, it's changing.
Oh, like
there is
what it means, yeah.
changing phi. I think
Yeah,
it's
yeah.
changing phi.
Yes. Yeah, oh yeah, you meant this, yes.
Yeah.
Yeah, so if you multiply by G on the left, that's the same thing as changing the realization
Yeah.
in that description. Because as Alan had explained, multiplying by is like, well, it is changing trivialization in the Pythagoras line. And and then there's a loop rotation version. X on all of these spaces. So just look that for their formula, T star X by weights. I mean, whenever you look at the quantum version, they take it so that like T star X by some half integral weight, but it wouldn't play a role today. I mean,
Well, only
okay.
yeah, it's with the traffic.
Okay.
I think this intersection is what people mean when they talk about ravioli in this context, gluing two copies of D over D star. I think, guys, are you talking about T over G cross NO? Yeah, but I think it's like less symmetric description. So you like flatten one of the. Yeah, I don't have a good picture in my mind, but you treat one of these differently. Right here, one got fixed to N0 to describe N0. Yeah, yeah, I think that's completely true, but yeah, I'm not sure. Yeah, so just like there is a more symmetric description where you look at this like it's something connected to this D cross D over D star, and somehow, sorry, yeah, this one. Yeah, D star. Yeah, but
Yeah, so some people call this raviolo. Because it's like you let this go along and implement the point. But like I guess Gus tried to really comment what it means, how it fits here, but actually I didn't understand.
Yeah, I guess if you start spelling out definition and flatten one of these, you get exactly this one condition is like one disk and another disk, but it's
I mean, like my first guess would be like if whenever you have something like this, GK, GO, GK, GO, and N or something, like it's
well.
Okay, I don't know. So yeah. Let me not try. Maybe I should. Okay, so like as you notice, so like FN Grassmann we saw was like some kind of thingy, like inductive, union of like finite dimensional varieties along some closed emergence. And these things are infinite rank vector bundles on them. So like, and we want to somehow talk about their like sheaves on them and like and their homology and such. So like, but you have to be careful clearly. And like, how do you do that? That's the next thing I'm going to talk about. Finite dimensional approximations. Okay, so let's recall a couple of facts from Elhan's talk. that the Alpine Grassmannian is a disjoint union over all dominant corates by Cartan decomposition of these open sugar cells. And if you take the closure of any dominant, if you take the closure of any, then that's the union. Well, okay, so disjoint union of all the mu that are bounded above by lambda, right? So these are called Schubert varieties. Okay. So and well, yeah, I mean, if you by simple arguments, I'm just gonna like brush it up, but like look at some points. I mean, we have some like huge group scheme acting, but look at what are the stabilizers. If I'm acting on some proper finite dimensional variety, I have to have some kind of very large stabilizer. So geo-action vectors through finite dimensional quotient on any of these finite dimensional ones. So our strategy, the first part will be restrict our vector bundles to finite dimensional bases given by these Schubert varieties. So we just write T less than lambda to be just a restriction to this closed Schubert variety. Same thing with R. So I can write it as less than lambda intersect R. And clearly these exhaust T and R. Yes. Okay. Okay. And then the second part. So having restricted the base to finite dimensional things, we want to look at finite dimensional quotients as fibers and then take inductive limits. So for positive integer b, consider fiber-wise translation by CB times NO. So NO is n and then power series. So this is something inside there. Is GK, GO, NO. Right? Then quotient. So quotient T by the image of this translation. And we get TD, which is going to be GKGO. But then now we have NO mod Z DNO. And I'll write the projection as pi D. Okay. And so this, I just like truncated the fibers to finite dimension, but we can combine these two strategies and restrict to finite dimensional base as well. For the closure. So now we have like a genuinely finite dimensional object. I have like a finite dimensional proper variety, and then projective variety, and then I have like a finite rank vector bundle on it. So this is genuinely a scheme of finite type. It's some vector bundle on projective variety. I have a fear that I'm going to run out of chocolate. Are there more chocolate?
Oh.
No, I can find it later. There's some. Oh, I'm good so far, but like I've used like half of it. Oh, thanks. Okay. Yeah. Yeah, and okay. So if D is larger than E, whenever that's the case, this or like these versions. So there are surjective homomorphisms of vector bundles, obviously, and their inverse limit clearly. Inverse limit is T or T less than 1. Thank you. Appreciate it. Okay, so that's good for T, but then like we have to be a little bit more careful.
Inverse limits.
Like so there are these maps whenever you have two integers, right? And it's a surjection of vector bundles. And I just take inverse limit, and then like it's just like taking inverse limit in the 5. So I just get NO because the intersection of these are 0. Is that it?
What I'm serious is inverse limit of CZ over CT. Definitions.
Yeah, and like I guess is yeah. Anyways, for R, we want to we're like slightly more rigid here, so we have to be really careful. Order of pole of En. So this was trivialization of D star R, whatever. So so by order of pole, what I mean is like what are the negative exponents of Z that occur if you write, I mean, this is a vector bundle trivialization. So like it's a matrix of some Lorentz series, and then you'll have some exponents of Z. And 0.
Of matrix of
phi n is just the Pn. Oh, Pn. So yeah. So that's a trivialization of a vector bundle. Oh, okay, infinite ranks you have to be careful about. Anyways. Okay. Let me know if anything's not clear. This is bounded by a constant depending on so like from some perspective it's kind of clear, but the thing to say I think is that lambda. So like remember the moduli description of affine Grassmannians, we have these G torsors over a disk and a trivialization over a punctured disk. But like we have these sub varieties, finite dimensional ones called Schubert varieties. So what are they? Well, open Schubert self corresponding to lambda is exactly the ones where like these so-called relative positions. So like how much the two bundles differ is given by this lambda. So think of GLN and then Z lambda 1, Z lambda n. Yeah, I mean, whenever like the difference between, I mean, the difference, I mean, the relative position is given by lambda. That's what these open Schur cells are, and then this comes from there.
It's an exercise. You
Yeah.
can write everything out explicitly. Everything.
Right. Okay. So why am I doing this? It's because I want to say that this part bounded by lambda in the affine Grassmannian is invariant under translation by ZD NO or ZD as soon as if E is greater than order of pole. So I can do the same thing as above. And this way define these things the same way. So just take the quotient by the translation in the fiber direction. And these are closed subspaces inside the things above.
Lines are more visible than T.
Oh, you just it's just that for R you don't want poles in the vector direction, right?
Oh, I see.
But you can kind of leave and make a pole. You just want to make sure that D is big enough, and then it will not happen.
And so the like these translations is the right action of the node in itself in this strictness.
Right action of what? Sorry.
What is translation by ZD? What is
Oh, like on each literally on each fiber
yeah.
of these vector bundles, you just translate. That's all. Like so, take some element here.
Yeah. Okay. By ZD. Okay.
Right. So like you translate by the same thing in every fiber, and then that gives an endomorphism of this vector bundle.
Yeah.
T.
I mean, I just understand quotient, but these translations, like, why are they well defined? Like,
Why are they
balanced product? I
Well,
mean,
sorry, what product?
why are they well defined in T? Like, T as pairs up to equivalence.
Well, I mean, but we also have this description.
Yeah, up to equivalence.
Well, I mean,
GS is equivalent to GD minus 1 DS.
sorry. Okay. Look at this. Sorry, look at this description. Yeah, sorry. Yeah, not yeah. There it gets a little confusing if you do this. Yeah.
Okay.
Yeah, sorry. Yeah, I should probably have pointed it out. Yeah, translate here.
Well,
Yeah.
yeah.
I mean that should make sense, right?
Yeah.
Yeah. Okay. So yeah, okay. So I mean there's some more things I could say along these lines, but let me maybe and So like this is like the finite dimensional approximation of our spaces that we're going to work with throughout. And these let us define equivariant Moore homology of R, which will be Coulomb branch algebra. All right. So let me say this. So on these restrictions and large enough D have actions on RD less than lambda, and then action by GO, but then vectors through some GI. So let me confuse O. Yeah, let me confuse the second of points and write like this. As a function for some large enough I. So if the action of vectors through some finite dimensional quotient. And so what's our strategy to define this object? We want to define it. The equivariant Moore homology. Okay, so we want to define the ones on less than lambda part, so that whenever I have some dominant relation, I get induced maps. Like the mu to less than lambda, and then I just take the direct limit of all of these things. So that's what we're going to do. So I have to define these less than lambda part.
We need to have maps this way.
Yeah.
And we
So
want the direct, and we want the inverse,
direct.
the direct limit of that to be that.
Yeah, that to be the Moore homology of R.
Oh, in the end, we want to find the
One for all without lambda.
as lambda go to.
Yeah, so I'm going to define this as Moore homology of R.
So as lambda gets like
For all dominant coeds lambda. For all dominant coeds. And that the direct system is given by the usual dominance relation. Okay, so as you might notice, like the whole setup is a little bit like well, it just takes time to set everything up. But I mean, that's what we're going to do today. So how are we going to define these like less than lambda parts? We're going to do it. We write it and then explain it. We're going to define them as the following. Well, what's Moore homology? What's the sorry? What's the some large integer?
Okay.
Yeah, I mean, I'm going to write some more and say a little more. So like covariant cohomology with minus in the usual thing. And then I want this is the dualizing complex. And then shift by the correct relation. So let me a second. DDNO.
So the dualizing sheet is in degree 0 or
It's a complex.
dimension?
Complex.
Do you shift it by the dimension of the complex itself?
It is, this is the dualizing complex, and then like I shift the homology by this degree. But a priori, this looks like it might depend on D and also on sorry. Also on I. The quotient that we apply. Well, the claim is that it doesn't. So why is that? Yeah, so this is modifying. For D large enough. And I depends on D. So why is that? So first for I, you have that if you have I and J, there are suitable numbers like here. Then what is this quotient? I think there was like some kind of similar argument in Elhan's talk, but these quotients are well just these. So and they're really quotient groups. Okay.
Malcolm tries to use it for negative number J, and I had questions about.
Oh, sorry, what? What was that?
Malcolm tried to use it for negative numbers. So if I use it for positive numbers, I guess it's
Negative numbers?
No, sorry. I think in your case it should be.
Yeah, I think for me, I think they have to be just calculated.
At least you can take like break it out and try the definition.
Right.
I think like it's basically all mods nuclei, but then you regard it as placed in Z to the J when you connect it to another like Z mod, another mod Z to the I primes.
Like it's sort of some of the newish map, like for if it's GLN, it's matrices.
So I was going to say, after this question, I'll just say, I mean, just think of G equals GLN as people would always do, and then just like some matrices with like coefficients in this weird vector space of finite finite. Anyways, so like some matrices, but the elements, if you take enough power of the entire matrix, it will become one. And that's the idea. Yeah. Okay. So, and then for D, so I mean, like it's like a slightly subtle thing, so I think it's good to think about it. So by the construction of this RD lambda, whenever we have D greater than E, so what's the relation of these spaces? Well, there are some vector bundles on the Schur variety, and there is a certain natural surjective homomorphism, and that is GO equivalent, obviously vectors. There's a finite group at variance. Okay. But it's locally trivial. Just look at the fibers. There's affine fibers. Dimension. Let's see, E and O mod the D and O. So, pretty standard argument. So, but the equivariant homology groups agree up to a shift by the dimension of the fibers. So, whether we use D or E, it's the same thing up to shift by, oh, okay, 2 times the complex dimension, so 2 then. Okay, so well, let's look at it again. Well, so if I replace E here, I would add something here, like exactly this, add or subtract. And then okay, so it's slightly okay, and then we could multiply it.
Wait,
It's like
wait, sorry,
yes.
I think, like, this is what we just wrote. So,
Yes.
Oh, okay, yes, yes, yes. Yeah, so like this is like a slightly confusing thing, so I want to say a little bit more. Any questions?
Yeah, what you just erased what holds for phi m, so this is kind of how we think about it. Let's see phi m on like this stabilization map on this less than number piece has some holes of about the degree when you add really large vector, three small, that's why the really large problem we see, and it doesn't matter. It still lies in this and all after
Right. Yeah. And so at once D is large enough, they give the same thing up to shifts.
Yeah.
Well, I mean, I think, yeah, it's like a slightly, well, I don't know, it's like a slightly tricky for me to say something informative, but like they've introduced this convention because of that kind of shift occurring in that definition, and it's like just tricky to handle it. So they, I mean, and I think I want to use this notation. I don't know how else to write it better. So so the degree of homology is okay. In a certain sense, relative to quote 2 times dimension of NO. Well, NO is infinite dimensional, obviously, but like, what does it mean? I mean, it's just going to be a piece of like a way of thinking or notation about these finite dimensional approximations that we'll just keep using. So what does this mean is so homology class of degree K in the equivariant form or homology means, what does it mean? Well, so we look at different D's, but means homology class and our D less than lambda degree, sorry, D large enough of degree A plus 2 times the dimension occurring over there. And O, the D, and O. So, okay. And the notation will be that I'm just following the paper's notation. We will just write 2 dim NO in the and similarly in similar contexts in shifts, etc. And it will always mean that we're actually thinking about these finite dimensional approximations and doing those specific degrees, but we just write it like this because otherwise it gets completely, you don't want to do that. Like bookkeeping gets too much. Is that good? So I'm just saying that I'll just write this in place of Okay, let me maybe write a little more and then,
Yeah, people like do plan to write this, like if you get an open orbit, that you get like an actual vector bundle over an open orbit, do plan to write that.
sorry.
Over an open orbit, over the Gödel
Oh, yeah, Ger lambda, okay.
Gödel lambda, exactly. Do plan to write that you want to have like an actual vector bundle over,
Like which one?
like R.
R?
R over, okay, well, maybe, if you don't, then don't, it's okay.
Okay. Yeah, I'm not completely sure.
Yeah.
Okay. Okay, so and separately, note so we have these closed immersions, closed immersions, for whenever mu is less than lambda, and for gives direct system as we want it. Is a direct system of Coulomb homology. Yeah, I think maybe it's yeah, should write that the these homology groups. So only homology is equivariant. Well, Coulomb homology for us. So as kind of familiar, we get that they get these actions. Similarly, for the loop version. That's right. So
Yeah, I guess I didn't tell about this, like, also didn't tell about it in the lecture, but this is standard construction, knowledge and formally, she didn't talk about it, but it's an action of homology or homology. It was a non-equivalent things and equivalent features to actually equivalent. It's not the standard products.
yeah, okay. So well, okay, that's well, anyways, chapter in the well, in the paper. So finally, we are going to, I mean, not yet, but like we're going to start defining Coulomb branches using the geometry that we just discussed. And where am I on time?
It's quite
Like, oh gosh, I'm doing. Sorry. Well, okay. Okay, so the task is to define and then study convolution product equilibrium Coulomb homology. And so just to give it away right away, it is going to be an associative, commutative, and unique pole. So that we can take a spec. So let me quickly recall, because it's helpful, I think. Okay, let me move this.
No, don't worry about it.
When no one is left in the room.
like commutative, do you mean graded commutative?
Just
So this one is commutative.
Oh, this is.
And call. I said, well, anyways, so how to define convolution product. If you have seen it, on the it's a tactic category. So like we're not gonna talk much about it, but like I'm going to write on things we do. And Alan mentioned there is this equivariant so this thing is called equivariant perversion on Angus one. That's called tactic category. Just name. Giving the symmetric monoidal product. Okay. So this diagram we will translate to our situation kind of convolution diagram and then use that to define convolution. So in the affine Grossmanian context, this is exactly this map. I mean this diagram. So GK is just product. And then so this twisted product just means K G O over G. We write this Q. And then do affine Grossmanian. So what are these maps? Well, GK I can quotient and go to affine Grossmanian. Here I just quotient. I mean, there's a natural quotient here, and then here, if you have something here, it is like GK times over GO of GK mod GO, and then you can take a product or define. It gives you something in affine Grossmanian. So, and then the construction is that, so if you have A1, A2 in the static category, like a short like this, what you do is you pull back, pull back of A1 of A2. And then, so, okay, I just said what the convolution diagram was in the for the static. And then we're going to do a similar thing. I'm just gonna, so just recall this notation whenever we have these oral constructions, we're going to write brackets. And then the product is the thing that's well defined. That's just like what we're going to remember. Just notations. And then, right? So here is a diagram. Is this enough space? Yeah, I think it should be enough space. So to the bottom part. So we call in some places I'm replacing GER and by T or R. T here and R here. And not yet, but like something like okay, so this is just an obvious match. Then we take the fiber product. And then, okay, so like write this as P, like this as Q. I should probably write this first. Now, the quotient by GO, by the direction. And then I multiply. And that thing should give me something in T as before. Multiplying something in GK, changing trivialization, can make me leave R and go somewhere in T. Okay, and then I have some things. Q, image of Q. And then tilde, and then this actually lands in R. Okay. So what you say? Right. Okay, so let me start from here. What are these maps? Like most of them are just like the obvious maps that you can write down. But oh, sorry. This is not working. So there's a pair. Maps to so the second R just project. And then GK to T, you want to act on the vector that well, let me write it. Q1 to 2S. Okay, and then second thing is just the same in R. This probably gets a little bit like too many things at some point. But if you like sit down and think about it, like well, most of them are just the obvious maps, I think. And you have to check that things are well defined, but then like the only thing to remember is that for brackets, product is well defined. Yeah, I'll just push it up. I'll go here.
Yes. You just wrote this. Yeah, this is the.
Okay, so the first thing to say is everything here is closed substack in here. Closed substack just means close on every test string.
Do you have a convolution for just for T, or you actually need R for that?
No, we want it on R, right?
No, is there a convolution for that?
On T? I mean, so well, first I didn't define, at least technically, I did think through, but I didn't define it on T, but maybe, I don't know, I haven't thought through it. I don't know if it makes sense or is defined or.
I would guess if you did all these definitions, then you would get like just there's one of G because you kind of cancel out this final.
But maybe, yeah, maybe. Yeah, like but I'm not like I didn't know for sure on this spot. Okay, so like, well, okay, like some sanity checks. I'm just going to skip because I'm like 3 out of time. But I'm just gonna say M is in number something you want. And maybe I won't write down formulas, but there are directions. Just look at the terms in the second row. Then there are group actions making all the maps equivariant, where so for the first two, we have two GOs acting together. And then there's a first projection to just GO, and then that acts here, and then GO acts here. And I mean, I should write formulas, but then maybe it's not that useful for everyone at this point. Or yeah.
Well, I guess we should define this equation. Yeah, sorry, what?
Oh, I just meant like the action for actions.
Exactly. Yeah, well, yeah, there's an issue.
Yeah, yeah. Okay. Yeah. Okay. So just do it here. So now we have all these formulas, all these spaces and this convolution diagram. And the object we're interested in is equivariant Borel-Miller homology on R. And I want to define some product on it. So we would naturally want to look at sheaves for complexes, in particular dualizing complex, and their homology, cohomology. So just need some generalities. Okay, so I'm just going to write very quickly because just recall. So any bounded constructible complex, we have these natural homomorphisms where these regular duality, and we're going to introduce an equation and these spaces don't have to be smooth. So yeah, I feel like I should say this, but like smooth normally means something finite dimensional. But our space, when I say some infinite type of thing is smooth, I roughly mean that it acts as if it's a smooth thing for sheaf and cohomology theories. And that is in the examples we have, that's going to be true because it comes from smooth finite dimensional things. But I'm not going to maybe spell it out in every case. But I just say smooth. They just say smooth, but yeah.
Pro smooth in nodes. Is that what was called pro smooth in nodes?
I'm not sure about the nodes. I didn't remember. Yeah, I mean the thing.
BFN just wrote smooth. BFN just say smooth.
Yeah, they just say smooth, and I mean, yeah, but like they're just a little. They just said it's smooth, but you have to make sense of what they actually meant. Okay. So I just thought I should make a comment because of that. So there's this construction that we will use for the convolution. So let's say I have something here, and some object here, and some object here. In a Cartesian diagram, BCDM, and then, okay, so pullback. We will define pullback / depending on the context restriction with support as this homomorphism. So what is it? The map from home of A and then at lower star B, which is of course just upper star A and then B. Then phi. So take some map from A to F lower star B here. And then I want to map that to something I'm going to write as F upper star, just F. I think that's their more or less their notation, which will be something from J upper sheet of A to J upper sheet of F lower star B. Why do you have such a map? Okay. Also, so if you take hypertopology, you get maps there as well. Yeah, like it's like some natural construction. Someone like forgot to copy it down and might not remember it. So okay, so right. Wait. Yeah. Okay. So what's happening is I have an object here and here. I have a map between them after push forward, and I want to get some map over here, upstairs, after push forward and pull back, obviously. Yeah.
Yeah, it's probably.
Yeah.
Or it's not.
Yeah, I mean, like I remember.
So you.
Well,
Yeah, I mean, what's more important, we can.
yeah, okay, maybe, yeah, maybe. So I'm moving it from downstairs to upstairs in the square. And to y.
Well, where do you, so X involved in this? Seems like when you go down this to. When you use X.
I mean, like in defining, which I didn't do.
No, but you mean, oh, you mean, okay.
Yeah.
I see. And it's on the.
Yeah. I could pull it up, but maybe if someone wants, I can just quickly look at it. We were kind of at least getting close to the convolution definition. Okay, one quick thing. Let me also just skip too much detail. Intersection pairing. In similar context, we always have just a recall, let's say. You dual and then homology omega. So what are we gonna do with this? So apply to this Cartesian square that we had in the left corner of the convolution diagram. Okay, left right is kind of switched, but so then a homomorphism, if we have some homomorphism, so look at this dualizing shift on this pullback, and then a map from that to just dualizing shift of this, let's say. Any such homomorphism will give gives a pullback with support, which will be so okay. So actually, this actually more or less spells out the construction of that thing. So this is the construction. So it's like the middle part is the construction of the map, and then they identify with what I'm writing down. So the point, well, okay, like lots of formulas, but like the point is really just that I have a map down here, I get some map up here and that's something I want in my construction. Yeah.
I mean, by default, you want to multiply homology classes, but I guess we will get homology classes.
Right. Well, yeah, the homology classes will be coming from homology of dualizing complexes with negatives. So that's what we're doing. Okay. At least if I understand. Okay, so we get spoiler. We get such a homomorphism that we need because we will see that in a moment that this thing is just a shift of this, and then we have some degree homomorphism of complexes. So we can do this one. Please still ask if anything. Geo equivariant complexes. So the first, maybe I forgot to write this. Okay, so let me write this. Compose with first and second projection and just write them as TTPR. So this map just compose both map to R, map to T, map to R. Okay, under that notation. R is constant sheaf of utilizing sheaf to go back on PT is utilizing a sheaf of constant sheaf and then shift it. Okay, so this is like an instance where we need this notation. So if recall, this just means that do the corresponding thing in finite dimensional approximations. And then together these give that from the product that's given by. So this is the thing that we want to get the full vector restriction. Okay, so 1 and 2 easily imply thing. So let me quickly say why this is true. Okay, so 1 is obvious because PR is just projection. The definition of PR in the convolution diagram. And then T2, it factorizes is from R, then B times higher here. So there's a map from this thing, R to NO, the vector part of R. And then let me write a PT prime. What is this? Well, and O, so quotient, and this is exactly T. So well, you have to check this is quotient, and this is the natural map from R to NO. I'll keep writing. Let me know if you have questions. So but since PT prime is just quotient, right? So PT prime has smooth fibers, infinite dimensional, mainly GO. So so what does it mean? By full omega T, that just well, I'm pulling on something smooth, so I just get omega N O and then -2 bringing GO. So if I pull from here to here, and this is T, this is this, but then this is smooth. So like this kind of looks smooth, but it's this one's actually like a little different nature than this. Yeah. Yeah. Okay. So I'm just saying that GK and then it's going to be a shift of the constant sheaf. B NO, and then I just shift by Q then NO minus, so and then I get -2 GO from here. Well, and then I just have to pull one more time, right? But then yeah, and then that gives me this. So there are all this I will share with the convolution products. Okay, so where are we? Well, we have we determine what this pullback of dualizing shift on the product T times R is. And then that gives some map like this, omega, like here to here, called pullback with restriction. And then, okay, so that's where we are. And then, we do have a map on hyperpolarization, which is just for a more knowledge equivalent. Okay, so we have, this is where we want to start the convolution, right? And then we have come back to something that looks like this. Actually, this thing is isomorphic under the pullback of Q tilde to HGO. In the convolution diagram, there was this part.
Yeah, I think you want to consume things.
Oh, yeah, I see. Sorry. Should not erase that. So like, well, I'm just kind of saying this is like of similar nature to this. You're just like pushing in one vector.
Like who creates this quotient where you quotient over the derivation?
Yes.
Okay.
Yes. And it's same type of integration keeper. And as until that is improper, we can push forward. Again. And then, so we're finally arriving for a long time at the convolution product. So same recipe as in that bucket. The convolution of C1, C2 and equivariant homology will just be push forward along multiplication. Choose full, and then this is iso, so I can take inverse, and then do full back of tensor products. And you can check it preserves gradient, the natural or homological gradient.
Does it?
I think so. That's my memory.
Huh?
That's my memory. Actually, you have to just, well, I mean, yeah, you have to check it. All right.
Ah, without any C stars and whatever.
Yeah, no, there's no C star so far. So I should say at least some things about it, although we're like
Yes, we can do 5 minutes.
5 minutes. Okay, yeah.
I mean, like in the beginning, I promised to people 6 p.m. and then we end each time at 5:30 because of like length of Webster's.
Yeah.
But I guess we can finish at 6 at some point, but maybe it's not we continue to do right now.
We do the 6, we should have a break.
Yeah, yeah. Okay, yeah. Go
Yeah,
ahead.
Were people like exhausted a while ago?
Yeah. Okay, I guess ending at least 6 is better here, but
Okay. Yeah, I'll wrap it up. So as mentioned above, before, so this gives is associative gradient ring and unit is a fundamental class of something inside R, namely fiber of R of the vector bundle R over 1 meaning 1 times GO. And okay, so the multiplication is linear over the G-equivalent homology of points in first variable. And I mean, okay, I'll say more. Same are true for the loop version, the quantum Coulomb branch. Okay, sorry. So we will. I mean, the notation is that this is A or AGN. And then, as we said at the beginning, the Coulomb branch will be the spec of A. All right. So in the if you add loop variable, then you just get some non-commutative ring, so you can't take spec. But well, it's something. This one's called the quantized Coulomb branch. Okay, so important is okay. I didn't say well. Okay, so A is commutative, and this requires proof. They give one proof in the paper. Okay, I'll just say once you do like a lot of work, it's short.
Alex should do it.
Oh, Alex is doing it. Okay, I didn't know.
Well, at least it's in the corresponding week of Webster's.
Oh, I see. I didn't know. Oh, okay. Yeah, I'll just quickly comment. There's another proof at the level of equivariant derived categories in a different paper. Just if you and I mean, and so this is at the level of homology, but there is like a more enhanced version. Am I missing anything that I should say? Okay, like I think maybe okay, so Alex is talking about like more geometric properties of convergence.
Yeah, flavor, conductivity,
like okay. Okay, that's good. Then I don't have to.
You could probably leave like a billion Coulomb branch to him and he will just not prove something in the end. So we have like 1 minute. So
oh wait, so what do you want me to write?
Sorry, what did you plan to do right now?
Oh, so wait, you would it be best if I write down the what's the result in the abelian case?
No, maybe it's not a good idea.
Too short, right? Yeah.
Yeah.
Maybe then I'll. Okay, so I'll just say verbally quickly for orientation that this is finitely generated over C. So in particular, it's going to be some Noetherian ring. So like it's a nice finite dimensional object. It's integral and also normal. So like has nice geometric properties like linear range, orthos, whatever. And then since we have a quantized version, the commutative version will have a Poisson bracket. And then like our Coulomb branch is singular, but like on the regular locus, maybe Alex will talk about it, but this thing is symplectic. Yeah. So I'll just end it there. Thanks for listening.
Yeah, any questions?
Any questions?
Can you define the cohomology or the equivalent cohomology aspect? Like, basically, the definition is taken as a limit, and I'm taking to a shape. Can you make it like just an abstract push forward for infinite dimensional things and say that that's a computation? Sorry?
What was it?
Can you define the cohomologies because you can always just define cohomology abstractly, like for int proper scheme, you can make like push forward points. Is that
Also, this thing is a limit. The space is a limit. It's not. I mean, like you're talking about RD less than lambda, right?
yes?
Okay.
So that like this stratification by like is that just a can you view just as a computation and not as a definition for it?
Do you see a way? Like,
I would guess that you can drop one of these things and try like to dualize in tree form. I think it's not really.
yeah, I guess if you use some more general foundation, maybe it's possible, but I don't know. Maybe you know. Yeah, I mean, but like it's something you have to be careful with. That's for sure. I mean, maybe there's like a more general reference. So.
Is it what happened in BFN? Like BFN
Yeah.
do this stuff? Okay.
Yeah, so everything is literally like a digest of BFN.
Yeah. Okay. Any
Zoom questions? Okay, well, yeah, I guess this.
any more questions? Okay, let's start again.